Hello everyone. This lecture is on hypothesis testing, which is an important part of inferential statistics. It often goes hand in hand with confidence intervals that we studied before. Now, a hypothesis test is conducted to replace an established belief or a statement with a new finding. For example, if there is an accepted population mean for a particular variable that has been there and that has been accepted as the appropriate mean for that variable for decades or even centuries, and then a new study comes up with a new mean and they claim that the established mean should be replaced with the new mean that came from the recent study, then they have to go through a process, a step-by-step process to show that they have strong evidence that the established mean is no longer valid or is not correct, and it should be rejected in favor of whatever the new mean is. All right, so in this chapter, we are going to learn about hypothesis testing, the concepts behind hypothesis testing, and learn the step-by-step process of of rejecting or accepting the established mean and replacing it with the new mean that came up from the recent study. Now, these are the topics that we are going to cover. We are going to talk about the nature of hypothesis testing, the concepts behind it, the approach we will take for the hypothesis testing. And then there are two approaches that we can use to complete a hypothesis testing and come to a decision. One is called the critical value approach, and the other one is called the p-value approach. Right, so we will talk in details about that, and then we will go through the entire process, the step-by-step process of performing a hypothesis test in under two circumstances. One is when the standard deviation is known, and it's not just the standard deviation that must be known. It's a particular standard deviation, that is the population standard deviation. All right, so one set of steps is when the population standard deviation is known or given to us, and there'll be another type of test when the population standard deviation is unknown or is not given to us. All right, so we will talk about all these topics in the following lectures. Now we'll start talking about hypothesis testing by first discussing what the types of hypothesis are. Okay, now we said before that a hypothesis test involves replacing what is called an established belief or an established measurement, all right, an established belief or an established measure. In statistics, most often it is the mean, the population mean. So it is an effort to replace an established belief or an established measure by a more recent measurement that came from a new study, perhaps. All right. Now, that established belief or that established statement that has survived for a long time, that's called the null hypothesis. All right. So, a null hypothesis is the hypothesis to be tested. We use the symbol H sub 0 to represent the null hypothesis. So the 0 in the subscript of H stands for null. All right. And the null hypothesis is the established truth. It is the established belief. It holds the population mean, perhaps, which has been there, which has survived for a long time. And now a more recent study coming from uh, an alternate hypothesis wants to contest the null hypothesis and replace it in favor of what's called the alternative hypothesis. So there is the established belief, and then we have what's called the alternate belief. That's a more recent measurement coming from a recent study which contests the alternate hypothesis, contests the null hypothesis, and attempts to replace it with its own measure, with the measurement that comes from its own study. So to define alternate hypothesis, it is a hypothesis to be considered as an alternative to the null hypothesis. We use the symbol H sub A standing for alternate, to represent the alternative hypothesis. All right. So again, keep in mind we have two types of hypothesis in hypothesis testing. There's the null hypothesis, which is the hypothesis that is considered, that has always been considered to be the correct measure or the correct belief, and that will get replaced. The attempt, it's not necessary that it will get replaced, but the attempt is to replace the null hypothesis by an alternate hypothesis derived from a more recent study. And that whole process, that whole exercise of deciding whether the alternate hypothesis can replace the null hypothesis or not is called the hypothesis test. So it's the problem in a hypothesis test to decide whether the null hypothesis should be rejected in favor of the alternative hypothesis. Now here's a pictorial view of the two types of hypothesis that we talked about previously. There's the null hypothesis on one side, that's the established hypothesis, the established belief in this case of statistics. It's the established population mean. It is the hypothesis that will get tested, that is going to get contested. And the symbol for it is H sub 0, where the 0 appears as a subscript of capital H. On the other hand, we have the alternative hypothesis. This is the hypothesis that will attempt to replace the null hypothesis with. All right, so it's called the alternative hypothesis. It is based on a more recent study. It is the alternative to the well-established null hypothesis. That's why it's called the alternative hypothesis. And the symbol to represent that is H sub A, where A is the stands for alternative. Now, the first step in performing a hypothesis test is to state the two hypotheses in a proper way. So we have the null hypothesis. That has to be stated first. That means you have to state clearly what the established hypothesis is, which is the null hypothesis. And the way we write it is this way here, H sub 0 and then colon. So H sub 0 colon and then the population mean, which is mu, equals mu sub 0. All right. So a few things here. A null hypothesis must always have an equal sign in the statement. Must always have equals in the statement. All right, now sometimes you will also find less or equal to or greater or equal to in some places, but the equals must always be there in the null hypothesis. And this mu sub 0 means the population mean that is already established, the population mean that goes with the null hypothesis, with the population mean that is the established mean. All right, so just keep in mind there has to be an equal sign in the null hypothesis statement. This mu sub 0 is going to get replaced by a value, a certain value, whatever the population mean for the null hypothesis is. And another thing that you must remember is that the null hypothesis statement must always be in terms of the population mean. All right, so you should always state your hypothesis with respect to the population measures. Must be in terms of the population measures. Terms of population measures. That means it has to be what are the metrics, how do we what is the term we use for population measures? It's parameters, correct? So here when stating your null hypothesis as well as the alternate hypothesis, we should always have population measures, all right, not sample measures. So you cannot write this as X bar, all right, it has to be mu. Now here's an example. It says a publisher claims that the mean of all statistics books is $175. You want to verify if that is true or not. So the established mean, according to a publisher, the established mean of all statistics books is $175. Now the fact that they have used the word all here, that implies population mean of all statistics books out there, according to a publisher, is $175. You want to verify if that is true or not. So we want to make sure if that is the correct mean or not using an alternate hypothesis. So the claim of the publisher will be considered as the null hypothesis, right? So $175 associates with the null hypothesis that is to be tested. So when we want to verify, that means we are questioning it, we are contesting it, and the statement, the way to state the null hypothesis would be null hypothesis. So H sub 0 colon mu equals mu sub 0. Now for this specific problem, because we have a value for what the population mean is for the null hypothesis is 175, we replace the mu sub 0 with 175. So for this particular example, we should write it as H sub 0 colon mu equals 175. Now you have to write the H sub 0 colon. Don't miss that. If you just write mu equals 175, the problem is that we won't know whether this is the null hypothesis or whether it is the alternate hypothesis. So make sure you always start your statement using H sub 0 colon, which says null hypothesis is mu equals whatever the mean, accepted mean is. Now to state the alternative hypothesis, you can do it in one of three ways. Now remember, the alternative hypothesis is contesting the established mean, the null hypothesis. And you can contest it in three ways. You can either say that the mean, the population mean, is not equal to whatever value it is, or you can say that the population mean is less than whatever the null hypothesis mean claims it to be, Or you can say that the population mean is greater than whatever the null hypothesis mean is. All right. So for the same example where a publisher claims that the mean price of all statistics books is $175, you claim that it is not true, right? That's the alternative hypothesis. That's the role of the alternative hypothesis that claims that the null hypothesis is incorrect, and you can make that claim in one of three different ways. One, you can say the mean price of statistics books is not equal to $175, or you can say the mean price of statistics books is greater than $175, or the mean price of statistics books is less than $175. So the way you write it out here is H sub A colon mu. Again, you have to use the population mean notation, is not equal, use the not equal sign, and then whatever the null hypothesis mean is, in this case it's $175. Or you can say greater than $175 or less than $175. Now it has to be one of the three. You cannot have multiple as the alternate hypothesis. It has to be one of the three. Now here's a pictorial representation of the three ways we can state an alternate hypothesis. So the first one we have is that H sub A colon mu not equal to mu sub 0 being the null hypothesis mean. So we don't know whether the population mean, the correct population mean, is less than the null hypothesis mean or whether it's greater than the null hypothesis mean. All we know that it is not equal to the population mean. In other words, it differs. All right, we think that the correct population mean is different from whatever the null hypothesis mean claims to be. The other one is that H sub A colon mu less than mu sub 0. Right, so here we are claiming that we know specifically that the null hypothesis mean is incorrect and that we think that the correct population mean is a value less than whatever the null hypothesis mean claims to be. And then finally we have the H sub A colon mu greater than mu sub 0. So here we are claiming that the null hypothesis mean is incorrect and that the correct population mean we think is greater than whatever the null hypothesis mean may be. All right, now associated with, so let me first write, just like I wrote differs here, let me write here, it's the less than, and then we have the greater than. All right, now associated with each of these statement types, we have what's called a tailed test. Now we'll go into tail tests in greater detail in future slides, but for the time being, just know that the tail test is related to the alternate hypothesis statements. When we have a not equal to in our alternate hypothesis, it makes it a two-tailed test. So what it means is, if I draw my normal curve, all right, then the null hypothesis mean will be somewhere at the center of the curve. All right, that's where the null hypothesis mean is located. And when we claim that it is not equal to, we are stating that the correct population mean could either be to the left, it could either be less than the null hypothesis mean, or it could be greater than the null hypothesis mean. So when we are claiming that the population mean, the correct population mean could be could be on either side of whatever the null hypothesis mean, then we are saying that it's a two-tailed test. That's what makes it a two-tailed test, because it could be on either side of the curve, the correct value. For the left-tailed test, so again, let me just draw the curve here. So we have our, again, normal curve. And again, the null hypothesis mean is located at the center. When we are saying that the correct mean, population mean, is less than, that means we are saying that the correct mean is located somewhere to the left. It's a value to the left of whatever the population, or sorry, whatever the null hypothesis mean is. That means it's a smaller value. It's less than whatever the current null hypothesis mean is. So when we do make that claim, it makes the test a left-tail test. It makes it a left-tail test. And then finally, when we claim it is greater than the null hypothesis mean, we are essentially saying, if this is where the null hypothesis mean is located, we are claiming that no, it's actually greater than whatever the null hypothesis mean is. It's located to the right. Right? So that's what makes it a right tail test. Okay, so for the time being, just understand that there is a tailed test type associated with each of these alternative hypothesis statements. Before I go further into the logic and process of hypothesis testing, I would like to draw an analogy of it with a court trial system. Now, in a court trial system, there are two parties. We have the defendant on one hand, and on the other hand, we have the prosecutor. And the prosecutor is the one who claims that the defendant is guilty, there's something wrong with the defendant, and the defendant needs to be locked up, or the defendant needs to be pronounced guilty, and some sentence needs to be passed on the defendant, correct? Now, in our justice system, as you know, the defendant is always considered innocent until proven guilty, correct? Until proven guilty. Now, just because somebody is saying that the person is guilty doesn't mean that the person should be thrown out. The prosecutor has to provide evidence against the defendant and prove that the defendant is guilty. Okay, so the prosecutor's job is to provide evidence against the defendant. Only then, and if it is credible evidence, if the evidence is strong enough, only then the jury system will decide if the defendant is guilty and make a pronouncement. All right? Now, given that premise, in the world of statistics, and specifically in the case of hypothesis testing, think of the null hypothesis to be the defendant. And just as the defendant is innocent until proven guilty, we always start our hypothesis testing with the assumption that the null hypothesis is true. There's nothing wrong with the null hypothesis. It has been there for many years, and it has been believed to be correct so far. All right, so we begin our testing on the premise that the null hypothesis is true. Now, the recent study that has produced what's called an alternate hypothesis claims that the null hypothesis is not true, correct? That's what the alternate hypothesis is testing or contesting the null hypothesis. However, it is the onus, it is the burden on the alternate hypothesis to provide evidence that the null hypothesis is incorrect. So what does the alternate hypothesis have to do? The same as what the prosecutor has to do. It has to provide evidence. It has to provide not just evidence, but an evidence which is strong enough, provide strong evidence against the null hypothesis. And where does the evidence come from? From the study. It comes from the sample study. So the alternate hypothesis has to provide all the metrics associated with the sample study. For example, the sample mean, the standard deviation, the sample standard deviation, as well as the z or the t values associated with the mean and the sample standard deviation, or the population standard deviation, as the case may be. So keep this analogy in mind, that the null hypothesis should be treated as a defendant, that the null hypothesis is true. To begin with, we always assume that the null hypothesis is true when we go into performing the hypothesis test. And then the alternate hypothesis is contesting the null hypothesis. It's trying to prove that it is guilty, and the evidence that the alternate hypothesis puts on the table comes from the sample study that it is based on. It has to bring to the table the sample mean, the sample standard deviation, and the associated scores, the z-score or the t-score, or later on we'll learn about other scores as well. But those are the metrics. Those will provide the evidence against the null hypothesis. And as we go through the process of performing the hypothesis test, eventually we'll come to a decision based on certain criteria whether the null hypothesis is true or it should be rejected in favor of the alternate hypothesis. Let's talk about the logic behind the hypothesis testing and on what criterion we decide whether the null hypothesis is going to be rejected or not rejected. Now, previously we said that the alternate hypothesis has to provide strong or sufficient evidence in order to reject the null hypothesis. And where does that evidence come from? It comes from the sample data. And if the sample data or the sample measurements are consistent with the null hypothesis, that means if the sample data is similar or close to whatever the null hypothesis states, then we do not reject the null hypothesis. All right, in that case, we say that the null hypothesis is pretty similar to what you are stating, what the alternate hypothesis is stating. So we will just keep the null hypothesis as is. The sample data is consistent with the null hypothesis. If, on the other hand, the sample data are inconsistent with the null hypothesis, which means that there's a big difference between what the alternate hypothesis came up with and what the null hypothesis was stating. If there's a big difference, then we reject the null hypothesis in favor of the alternate hypothesis. So that's going to be our logic behind our decision on whether the null hypothesis should be kept as is, that is, do not reject the null hypothesis, or whether we should reject it in favor of the alternate hypothesis. Now, in the process of the hypothesis testing, when we decide whether the null hypothesis should be rejected or not rejected, we can be susceptible to making some errors. And there are two types of errors possible in the process of taking a decision. They are called the type 1 and type 2 errors. Now, type 1 error is when we reject the null hypothesis when it is in fact true. So, if the null hypothesis is true, but the evidence from the alternate hypothesis has been misleading us, and we end up rejecting the null hypothesis, then what we've done is we've made a type 1 error. All right, that means where the null hypothesis is in fact true, but we ended up rejecting it because the evidence kind of misled us. The other one is type 2 error, where we do not reject the null hypothesis when it is in fact false. So that means that the null hypothesis out there was in fact not true, it was false, but the evidence was not strong enough, and we ended up not rejecting the null hypothesis. We just kept it as is. So these are the two types of errors. Now in the next slide, I have a table which may make it easier for you to remember the two types of errors. So let's go into that. Now here's the decision chart that I was talking about in the previous slide. So let's look at it. It may be easier for us to understand what the type 1 and type 2 errors are. So here we have the two possible decisions taken on the null hypothesis. The decision is always taken on the null hypothesis. And the first one is do not reject null hypothesis, and the other one is reject the null hypothesis. And here we have across the two states, possible states of the null hypothesis, which is true or false. So either the null hypothesis could be true or it could be false. Now, previously, when we were comparing the hypothesis testing to a court trial situation, we said that the null hypothesis can be regarded as the defendant, correct? We can compare the null hypothesis to be similar to a defendant in the court trial situation, and a defendant is always assumed to be innocent to start with. All right. So if the null hypothesis is true, if it is innocent, true, and we do not reject the null hypothesis, that means we have taken the correct decision. So let's say if the defendant is really innocent, but and we pronounce him innocent, that means we do not uh, 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 do not sentence him or do not claim him or her to be um, guilty, then we have taken the correct decision, right? If an innocent person should not be pronounced guilty, we do not reject the null hypothesis in a case of hypothesis testing, and we've taken the correct decision. If, on the other hand, the null hypothesis is true, but we have rejected the null hypothesis, then we've made an error. That means we have proclaimed the defendant that was innocent, true, innocent, to be guilty. We've rejected the null hypothesis. We've made an error, and that error is type 1 error. Now, I can give you a mnemonic to remember this. Think of the type 1 error, this I here in the type 1 error, to be innocent. All right, so you can just think of that I as innocent. So that means the null hypothesis is innocent, but we have rejected it. That's type 1 error. All right, in a type 1 error, the null hypothesis always is true. It's true, but we think it isn't true. we have rejected it. The other case is when the null hypothesis is false. In other words, the defendant is really guilty. The defendant is guilty. The null hypothesis is in fact false, and we do not reject the null hypothesis. That means a guilty defendant, if he or she is not pronounced guilty, we do not reject the null hypothesis. We do not proclaim it as wrong. Then we've made an error in our judgment, and it is considered to be a type 2 error. If, on the other hand, the null hypothesis is false and we have rejected the null hypothesis, that means we have taken the correct decision, right? The person or the defendant was guilty, false, guilty, and we have decided that the person is guilty. That means we've rejected the null hypothesis, rejected the defendant, all right, and sentenced him or her as guilty. Then that is the correct thing to do. It is the correct decision, right? So you have to remember these two types of errors possible. For a type 1 error, null hypothesis is always true. For a type 2 error to happen, the null hypothesis should be false. Okay? Now that we have talked about the two possible types of errors in making a decision on the null hypothesis, let's look at the probabilities of making such errors. All right. Now, the type 1 error is when the null hypothesis, so let me write that down here. The type 1 error happens when the null hypothesis is true and we reject it. So that's an error in our judgment, and we should always keep the probability of that error happening very low as we can. So probability of a type 1 error should be kept low. We do not want to sentence an innocent person as guilty, correct? That's wrong. So that probability should be kept low. Now, that probability of making a type 1 error is called the significance level in statistics, especially in hypothesis testing. A significance level implies the probability of making a type 1 error. That's the term we use for the probability of making a type 1 error, which is rejecting a true null hypothesis. And the notation we use to represent the significance level is alpha. All right. So the significance level in hypothesis relates to type 1 error. So significance level has to do with type 1 error. What is it? It is the probability of making a type 1 error, that is rejecting a null hypothesis when it is true. The probability of making this error should be kept low. Okay, so again over here it says the probability of making a type 1 error, that is of rejecting a true null hypothesis, is called the significance level alpha of a hypothesis test. Now, when we learn how to perform a hypothesis test step by step, this significance level alpha is going to come into play when taking a decision. There are going to be two approaches we will learn to perform the hypothesis test with. And in one situation, alpha will represent the cutoff point between rejecting a null hypothesis and not rejecting a null hypothesis. So we'll go over that in the next few slides, all right? Now we just said that the significance level is the probability of making a type 1 error, right? Significance level is denoted by the letter alpha, and it is the probability of making a type 1 error. Making a type 1 error. So what is type 1 error again? It is rejecting a true null hypothesis. Which is rejecting a true null hypothesis. That's what type 1 error is. And the significance level always has to do with the type 1 error. Type 2 error is when we do not reject a false null hypothesis. So let me write that down here. Type 2 error is not rejecting a false null hypothesis. Not rejecting a false null hypothesis. That's what type 2 error is. And the probability of making a type 2 error is denoted by the symbol beta. All right, so let me write that down a little more clearly. All right, so alpha has to do with type 1 error, and beta has to do with type 2 error. Both represent probability values. Again, probability means area, correct? Probability is area. So alpha represents probability, but it's the probability of making a type 1 error, and beta also represents probability, but it's the probability of making a type 2 error. Now in type 1 error, null hypothesis is true. In a type 2 error, the null hypothesis is not true. It is in fact false. Okay, it is false. So let's see what it's saying here. It says the relation between type 1 and type 2 error probabilities for a fixed sample size. The smaller we specify the significance level alpha, that is the probability of a type 1 error, the larger will be the probability beta of not rejecting a false null hypothesis. So there is a kind of a relationship between the alpha and beta. The, the lower you keep the probability of making a type 1 error, you have a higher probability of not rejecting a null hypothesis which is false. Okay. Now, towards the end of a hypothesis test, we have to draw some conclusions and then come up with an interpretation of the hypothesis test we performed. So it says here the possible conclusions for a hypothesis test is, suppose that a hypothesis test is conducted at a small significance level. Again, significance level is the probability of keeping the type 1 error low. So if it is performed at a small probability of type 1 error, then if the null hypothesis is rejected, we conclude that the data provide sufficient evidence to support the alternative hypothesis and therefore reject the null hypothesis. And if the null hypothesis is not rejected, we conclude that the data do not provide sufficient evidence to support the alternate hypothesis. All right. So when we write the interpretation at the end, at the last step of our hypothesis test process, when we write the interpretation, we have to phrase it so that we say that the data either provide sufficient evidence if we have rejected the null hypothesis, or we have to say that the data did not provide sufficient evidence to reject the null hypothesis and replace it with the alternate hypothesis. So we will go through some exercises where we will learn how to phrase the interpretation correctly. All right. Now, there are two approaches to performing a hypothesis test. The first one is the critical value approach, and the other one is the p-value approach. We will learn about that a little later, but first let's talk about the critical value approach, which is also in short referred to as the CV approach, and I may refer to it from time to time in its short form, which is the CV approach. All right. Now, what the critical value approach does is it provides a cutoff between rejecting a null hypothesis and not rejecting a null hypothesis. So, a critical value, as the name suggests, is the critical point at which a null hypothesis may get rejected or will get rejected. All right, so that's why it's called the critical value. It's that critical point at which the null hypothesis will get rejected. So as we see in this picture, there's a standard normal curve and there are two regions, all right, around a certain point on the curve. All right, so how do we decide at what point the null hypothesis will be rejected versus not rejected? That point is decided or determined by what we just learned to be the significance level. All right, the significance level tells us where the cutoff is going to be on a standard normal curve. What is the significance level? It is the probability of rejecting a true null hypothesis. And we said that the null hypothesis, the probability of rejecting a true null hypothesis should always be kept low. And that probability is denoted by alpha. So what is alpha? Alpha is an area under the curve, which is the probability of making a type 1 error. Now, since we try to keep alpha low when performing a hypothesis test, it usually takes a value of 0.05 or 0.01 or sometimes even values less than that. All right, so in this example, we'll see that they have used an alpha value of 0.05. Now, 0.05 when converted to a percentage point is 5%, correct? 0.05 is the same as 5%. So you will see often that a significance level is stated in percentage points. That means it'll say that a hypothesis test should be performed at 5% significance level, which means that the alpha value is its decimal form, which is 0.05. Now, how does this 0.05 decide the cutoff between the reject and the do not reject region? As we said, since alpha represents the probability of making a type 1 error, that means rejecting a true null hypothesis, the area of the reject region under the curve is going to be that particular alpha value of 0.05. So the cutoff is going to be at the point on the curve where the area is 0.05 of the reject region. And then to come up with that exact critical value, the cutoff value, it's going to be z of whatever alpha is, z of 0.05. Now, if it is on the left-hand side, if the reject region is on the left-hand side, as in this case, the z value is going to be negative. So negative z of 0.05, if you look up your table, it will be negative 1.645, and that's why they have negative 1.645. Again, keep in mind that the standard normal curve is always based on the z values, is always upon the z line here, the horizontal line, is scaled with z values, 0 being at the center, all negative values, z values to the left of 0, and all positive z values to the right of 0, right? So we have here now the reject region on the left and the do not reject region on the right. Now, since the reject region is to the left, that means that this is a left tail test. We could have a reject region also on the right hand side. All right. We could have reject on the right hand side too, and do not reject region on the left hand side. When do we have that? When we have a right tail test. All right, remember, if you go back to the beginning of this lecture, we talked about a left tail test, we talked about a right tail test, and we also talked about what's called a two tail test. All right, if it's a left tail test, that means the alternate hypothesis has a less than symbol in its statement. If it is a right tail test, then the alternate hypothesis has a greater than symbol in its statement. And if it's a two tail test, it has a not equal to symbol in its statement. So let's quickly run through this particular diagram here. It says rejection region, non-rejection region, and critical value of a certain hypothesis test. So we have the rejection region on the left-hand side, and then on the right-hand side we have the do not reject null hypothesis, and this value which creates the cutoff between the reject and the do not reject is negative 1.645, which is negative z of alpha. So what is alpha? Alpha is 0.05, and that's a value which will be given to us in most of the problems that you have to test, but the significance level will be given to you. All right, so you will know the alpha value, and you will be able to come up with your critical value from there.
Continuation of the critical value approach. So I'll be summarizing what I spoke about this approach in the last few slides. It says here the critical value approach consists of a critical value. So we said that we are going to work with our normal curve. A normal curve runs over the z line, right? The z value line. And with the critical value approach, there's going to be a critical value which is the cutoff between the rejection area and the non-rejection area. All right, so what is the critical value? The critical value are the value or values of the test statistic that separate the rejection and non-rejection regions. A critical value is considered part of the rejection region. All right, so it's a cutoff point. So if it is a left tail test, then let's say this is the cutoff, the z value, which separates the reject region from the do not reject region, and let's say that we got a z value cutoff of negative 1.645. If the cutoff is on the left hand side, then your z value will be a negative value. All right. And the thing is that if your test statistic, that is, if your evidence, the test statistic that you obtained from your sample study is a value that falls in the rejection region, then we will reject the null hypothesis in favor of the alternate hypothesis. If it falls in the do not reject region, then we will keep the null hypothesis as is. We will not reject it. So here it says the rejection region, which is all this area to the left-hand side in this particular picture. It says it is the set of values for the test statistic that leads to rejection of the null hypothesis. So any test statistic that will be along this part of the line from the extreme left-hand side to this negative 1.645 value, which is the critical value, will mean that the null hypothesis should be rejected. If our test statistic falls on the right-hand side of the CV, which is the do not reject region, then that means we will not reject the null hypothesis. So it says the non-rejection region is the set of values for the test statistic that leads to non-rejection of the null hypothesis. And of course, the critical value is the separator. It divides the curve into a reject region and do not reject region. And the critical value is considered part of the rejection region. So if you get a test statistic which is negative 1.645, then we still reject the null hypothesis, right?
Now in this slide, we show the rejection regions based on the hypothesis, the alternate hypothesis, all right? It will be determined, the rejection regions are determined from the alternate hypothesis statements. The reject regions will always be at the ends of the curve. If it is a two-tailed test, the rejection region will be on both ends of the curve, and the region in between will be the do not reject region. All right, do not reject the null hypothesis region. Okay, now since the critical values are obtained from alpha, right? Critical values are obtained from alpha. For a two-tailed test, we have to split alpha into two equal parts. So for two-tailed tests, alpha will need to be divided equally between the two ends. Alpha divided by 2. So the area of the reject regions in the two-tailed tests will be alpha by 2. All right, that's the area. Alpha by 2 represents the area. However, the actual critical values are going to be z of alpha by 2 or t of alpha by 2, depending on which test we are performing. For a left-tailed test, the reject region will be on the left-hand side, all right, on the left end of the curve. And the right-hand side, the other side, is of course the do not reject null hypothesis region. Again, the area of the reject region is alpha. In a one-tailed test, whether it's left-tailed or right-tailed, we do not need to split alpha into two equal parts like in the two-tailed tests. All right, so it's going to be alpha, and the critical value is going to be z of alpha by 2. In this case, actually, if it's a left-tailed test, it's going to be negative z of alpha by 2. All right, so here for the two-tailed test, we are going to have two critical values. One is going to be negative z of alpha by 2. The other side, on the right-hand side, it's going to be positive z of alpha by 2. For a left-tailed test, it's going to be negative z of alpha, not alpha by 2, but negative z of alpha. And then for a right-tailed test, the reject region is going to be on the right-hand side. The area corresponding to the reject region is going to be alpha as well, and the critical value, the critical value is going to be a z value, but z of alpha, whatever alpha is. Now we talk about how to obtain the critical values. We've already spoken about it, but here let's formalize it. It says obtaining critical values. Suppose that a hypothesis test is to be performed at the significance level alpha, then the critical value must be chosen so that if the null hypothesis is true, the probability of is alpha that the test statistic will fall in the rejection region. What does this mean? Now, we know that the critical value is going to be obtained from alpha, correct? So obtained from alpha. And what is alpha? Alpha is derived from the significance level at which we are testing. So if the significance level is a 5% significance level, then the alpha is the decimal form of the percentage significance level. All right, so the critical values are obtained from alpha. Always keep in mind that the critical values are going to be a z value or a t value. All right, it's going to be a z value or a t value. How do we find a z or t value? It has to be based on alpha or alpha by 2, as the case may be in a two-tailed test. So we have to know what alpha or alpha by 2 is, and then we have to go to our tables to get the corresponding z values. So critical values obtained from alpha. What does alpha signify? Alpha means is the area of the reject region. Okay, alpha represents the area of the reject region. It also implies the probability of making a type 1 error. Probability of making a type 1 error. And what is a type 1 error? It means rejecting a true null hypothesis. A true null hypothesis. All right. So the way we go about finding the critical value is first find alpha. All right, we first find alpha and then we use that alpha, take it to the z table. Now if it is a t-test, then we go to our t-table with the appropriate df, degrees of freedom, and we find the z value or the t value for that particular alpha or alpha by 2, as the case may be. Now once again, here are the three curves for the three possible tail tests for a hypothesis. The first is the two-tail test, and it says here the critical values for one mean z test at the significance level if the test is two-tailed, left-tailed, or right-tailed. So as we see here, whether we're going to have a two-tail test or a left-tail test or a right-tail test will be determined, as I said before, it will be determined from the alternate hypothesis statement. If the alternate hypothesis statement says mu is not equal to, if there's a not equal to sign in the alternate hypothesis, that means it's going to be a two-tail test. If it says, if it has a less than sign, all right, in the alternate hypothesis, then it's going to be a left-tail test. And if it is mu greater than, if there's a greater than sign in the alternate hypothesis, all right, all this has to do with the alternate hypothesis. Keep in mind that the null hypothesis will always have an equal sign in it. So if it is greater than, then we will end up with a right tail test. So for a two-tail test, you see, we have reject regions on both ends of the curve. And the areas of the reject region is alpha by 2. So for a two-tail test, we have to divide alpha into two equal parts, and they will represent the areas of the reject region at each end. The center region is do not reject null hypothesis. Now for the critical value, the critical values, as I said before, is either a z value or a t value. For the left end, the critical value in a two-tail test is going to be negative of z of alpha by 2, and on the right end, it'll be a positive value for z of alpha by 2, right? Because all values to the right of 0, all the z values to the right are positive values. All the z values to the left of the center point 0 are going to be left values. So when you find your z values, make sure if it is on the left hand side, you're writing it as a negative value. On the right hand side, you're writing it as a positive value. For a left tail test, we do not need to split alpha. All right, we do that only in the case of a two-tail test. If it is a one-tail test, whether it's left-tailed or right-tailed, we do not need to split alpha. We just keep it as is. Again, alpha is always the area of the reject region. So if it is on the left-hand side, it'll be a negative z of alpha. For a right-tail test, the reject region is to the right. Alpha is also to the right because alpha always goes with the reject region. All right, and the cutoff point, the CV critical value, is z of alpha. So now keep in mind again that critical values are z values or t values. They are not areas. All right, we find critical values using the alpha values, but critical values are not alpha values. They are z values or t values. Now we'll talk about the other approach in hypothesis testing, and it's called the p-value approach. Now the P stands for probability. So I'm going to explain a little bit what this p-value is about. It says here the p-value of a hypothesis test is the probability of getting sample data at least as inconsistent with the null hypothesis and supportive of the alternative hypothesis as the sample data actually obtained. We use the letter P to denote the p-value. So it's actually to do with the probability. But I understand that just by reading it, it's not easy to conceptualize. So let me just start with an example. Now, what it is saying is, for in a p-value approach, we assume that the null hypothesis is true. So we begin with the assumption that the null hypothesis is true. So given that the null hypothesis is true, what is the probability? All right, so let me just write that down here. Given null hypothesis is true, what is the probability of getting a test statistic inconsistent, all right, inconsistent with the null hypothesis? All right, again, I'm going to stop here, pause here, and go back to explaining what we understand by inconsistent. Now, when we were talking about the logic behind hypothesis tests and making a decision, we said that if the test statistic data is consistent with the null hypothesis, then we do not reject the null hypothesis. If, on the other hand, if the test statistic data is inconsistent with the null hypothesis, then we reject the null hypothesis. All right. What is test statistic? Test statistic is the evidence that you put on the table. Test statistic is obtained from your sample data. All right. It's the z value that you derive from your sample study, z or t or whatever distribution we may be using. All right, so test statistics comes from your sample data, and if we see that the test statistic is very different from the null hypothesis measurement, what the null hypothesis is stating. Inconsistent means if it is far off from the null hypothesis metrics, then we will reject the null hypothesis. All right. So in the p-value case, in the p-value approach, what we do is we start with our test statistic and we try to find the probability of getting that particular test statistic given the null hypothesis is true. All right. And then if we see that the probability of getting that test statistic is very low if the null hypothesis is assumed to be true, then we will reject the null hypothesis. Otherwise, if it's not that low, then we think we believe it will be consistent with the null hypothesis, and we do not reject the null hypothesis. Now, I have posted a video, a YouTube video actually, where they explain the concept behind the p-value using an example of flipping a coin. All right, so I strongly encourage you to watch that YouTube video, and they will explain there quite well how they decide that that the null hypothesis may not be true, all right, based on the probability of getting a test statistic. All right, so please watch that video because it will really help you understand the concept behind the p-value. So in the p-value approach, what we do is we start with the test statistic. So you start with the you don't have to divide your break up your curve into rejection region and do not reject region or find critical values. The process for the p-value is find area, which is also the probability. All right, find the area or probability of your test statistic, and then once you find the area, you compare your p-value. That area is your p. All right, compare p-value with alpha. If p-value is less or equal to alpha, then we reject the null hypothesis. Otherwise, if it is greater than alpha, we keep the null hypothesis. We do not reject it. So that's going to be the process of using the p-value approach. But we will talk about it later, and I will work through some example problems also on how to apply the p-value approach. Now here's a graphical representation of the p-value. We still have the normal curve with the null hypothesis mean at the center, all right? And over here we see z equals, right? We have a point here on the left hand side which says z equals negative 2.65. Now keep in mind this is not a cutoff. You see over here there are no reject regions or do not reject regions or no critical values. Z equals negative 2.65. This is a test statistic value. All right, so this is here is a test statistic value that was obtained from your sample mean, your standard deviation, and so on. All right, so it's a test statistic value, and what we do is we mark that on our curve, that particular value. We see it'll be to the left hand side, way off to the left from 0. And what we do is we find the area corresponding to that z value. All right, we have to find the area corresponding to the z value. Now, if it is a left tail test, then we will look for the area to the left of that particular z value. If it is a right tail test, if this was a positive 2.65, then 2.65 would be located here on the curve, on the right hand side, and we would be interested in the area to the right of 2.65, which would be, that area would be the p-value. So p-value represents area, an alpha value, all right? Well, it's not the significance level alpha value, but it represents area, all right? And area can also imply the probability. So what it tells us, the p-value tells us, is the probability of getting a test statistic of this measure given that the null hypothesis is true. That means the true null hypothesis will be located at the center of the curve. So given that the null hypothesis is located at the center, that means it's true. What is the probability of getting a z-value from our sample study, that is the test statistic of this measure? How do we find the probability? We have to go to our table or use our graphing calculators to find the corresponding p-value. Now, if it's a left tail test, then the p-value will be located to the left. If it is a right tail test, the p-value will be located to the right. If it is a two-tail test, then the p-value will be 2 times whatever the area is on one side. All right. Now, once we obtain the p-value for our test statistic, how do we decide whether the null hypothesis should be rejected or not rejected? All right, so what is the decision criterion for p-value approach? It says here is, if the p-value is less than or equal to the specified significance level, then reject the null hypothesis. Otherwise, do not reject the null hypothesis. In other words, if p is less or equal to alpha, reject null hypothesis. Otherwise, do not reject null hypothesis. So basically, we find the area corresponding to our test statistic and corresponding to the tailed test that we are performing. And then once we find a p-value, the next step would be to compare p with alpha, that is the significance level that we are using. All right, and if p, so we compare, if p less or equal to alpha, reject null hypothesis. All right, and if p greater than alpha, then do not reject null hypothesis. Do not reject. So that's what our decision is going to be based upon. Now we'll wrap up our study of the p-value approach in the next few slides here. So this is just summarizing what we already talked about determining a p-value. So let's read through it. It says, to determine the p-value of a hypothesis test, we assume that the null hypothesis is true, right? The null hypothesis is true. Therefore, in our curve, then if the null hypothesis is true, it should take the center point on the curve. The null hypothesis should be placed at the center, the null hypothesis mean. All right. And then we assume that the null hypothesis is true and compute the probability of observing a value of the test statistic as extreme or more extreme than that observed value. So we start with assuming that the null hypothesis is true, and given that the null hypothesis is true and located at the center of our curve, we take our test statistic value and see how far it is off from the null hypothesis mean. So if it is located at an extreme end, it could be on the left hand side, it could be on the right hand side. If it is located at an extreme end, okay, the further it is located on the curve or on the towards the ends of the curve, the lower probability it will have, right? The area gets smaller and smaller as we go towards the ends of the curve, correct? So if the test statistics is located far off from 0, all right, then that means the probability is going to be low for that test statistic. All right, so it's going to be an extreme value. So by extreme, we mean far from what we would expect to observe if the null hypothesis is true. All right, so that's what the p-value is about. All right, so is about the determination of the p-value is. Now, just like we had drawn the diagrams of in the critical value approach, remember in the critical value approach, we had 3 different graphs for two-tailed, left-tailed, and right-tailed. And then we had, however, reject regions and do not reject regions. In the p-value approach, you will not find a reject region and a do not reject region in any of these pictures. Instead, you will have areas, but those areas on the extreme ends will represent the p-values. So the two-tailed test, the p-value will be on both sides. All right, so your test statistic, this negative z sub 0 and positive z sub 0, would be your test statistic value, your test statistic obtained from your sample study. So the p-value is the sum of these two regions, shaded regions. For a left-tail test, the p-value would be on one side. So for a left-tail test, most likely your z-value, your test statistic value, would be a negative value. So it's area to the left is what the p-value would correspond to. For a right-tail test, the z-value would be a positive value, so it would be on the right-hand side of 0, and the p-value would be the area to the right of that particular z-value. So let's say we came up with a test statistic value of negative 1.19, and test statistic is always a z-value or a t-value. It's not the actual sample mean value, it will be the corresponding z-value of the sample mean and the standard deviation based on the sample mean and standard deviation that came from your sample study. So we locate that particular test statistic value on the normal curve with respect to the null hypothesis mean, which will be located at the center. And then if it is a left tail test, we have to go ahead and find the area corresponding to z of negative 1.19, and it'll be the area to the left of that particular test statistic. And that will be if it is a left tail test, right? Again, like I said, we will go through a few examples where I will show you how step by step we perform the test using the two approaches. Now here's a compilation of the steps to use the p-value approach. The first 3 steps are common to both the critical value approaches and the p-value approach. All right, these first 3 steps are common. So step 1 says state the null and alternate hypothesis. Step 2, decide the significance level alpha. Step 3, compute the value of the test statistic. All right, so these 3 steps apply to the critical value approach as well. But from step 4, for the p-value approach, we have to determine the p-value from our test statistic. So we have to take our test statistic, and based on whether it's a left tail test or a right tail test or a two tail test, we have to refer to our table or our calculators to find the corresponding area based on the test statistic value. Right? And once we find our P, we compare it with alpha. If P is less or equal to alpha, then we reject the null hypothesis. That means the P value is low enough. That means the test statistic is inconsistent with the null hypothesis if it were true. So if P is less or equal to alpha, reject null hypothesis, otherwise do not reject the null hypothesis. And then step 6, we have interpret the results of the hypothesis test. Now, step 6 again is common to both the critical value and the p-value approaches. Now, one last thing about the p-values. The value of the p that we find from our test statistic, just by looking at the value, we can sometimes tell how strong the evidence is against a null hypothesis. If p is greater than 0.10, so if our p value is a value greater than 0.1, that means it's weak and it has weak evidence against the null hypothesis. In that case, we do not reject the null hypothesis. If the p-value is a value between 0.05 and 0.10, then it's said to have a moderate evidence against the null hypothesis. So we would still not reject the null hypothesis. In that case, we would need to compare it with alpha. All right. If the p-value is a value between 0.01 and 0.05, that means it's a pretty strong evidence against the null hypothesis. Therefore, we will end up rejecting the null hypothesis, and if it is a p-value less or equal to 0.01, it's very strong. So in the last two cases, when the evidence against null hypothesis is strong or very strong based on the p-values, then we do not need to compare it with alpha. Sometimes they don't compare. Statisticians won't compare it with alpha to come to a decision. If the p-value is greater than 0.10, then just right away looking at the p-value, they would know that there's not strong evidence. The evidence against null hypothesis is weak. They will not reject the null hypothesis. Decision will be do not reject. And for a case of where the p-value has moderate evidence, it would be left up to the discretion, but more often than not, it would be do not reject. All right, so here it says many researchers do not explicitly refer to significance levels. Instead, they simply obtain the p-value and use it, or let the reader use it, to assess the strength of the evidence against the null hypothesis. So that step where we compare the p-value with alpha doesn't need to be done based on this table here. If p is greater than 0.1 outright, we know that null hypothesis cannot be rejected. The evidence is weak. If the p-value is a value between 0.05 and 0.10, it's moderate evidence. Therefore, we still do not reject null hypothesis. If it is strong, that means if it is a value between 0.01 and 0.05, we will end up rejecting the null hypothesis, as well as if it is if p is less than 0.01. Here are the 6 steps of performing a hypothesis test using the one mean z-test. Now keep in mind we use the z-test when the population standard deviation sigma is known. So the purpose is to perform a hypothesis test for a population mean mu. These are some of the assumptions. The first one is common for all tests, simple random sample. all statistical studies have to be based on a simple random sample. Then it has to be a normal population or a large sample. And then finally, sigma, population standard deviation, should be known. Now, if all these assumptions are satisfied, then the first step is to state your hypothesis. And you have to state both the null hypothesis and the alternate hypothesis. The null hypothesis, the way you're going to write it is H sub 0 colon, and then mu, the population mean, is going to be whatever the null hypothesis mean is or has been. Alternate hypothesis can be one of these three. It would either say that mu is not equal to mu sub 0, that is whatever the population or rather whatever the null hypothesis mean is, or it could be that mu is less than the null hypothesis mean, or it could say greater than null hypothesis mean. And based on how the alternate hypothesis is stated, it would be a two-tailed test, a left-tailed test, or a right-tailed test. In step 2, we decide on the significance level alpha. For our purposes in this course, alpha will be given to you as a significance level of 5% or 1% or in percentage form. The alpha value is the decimal form of that percentage. All right. And then step 3 says compute the value of the test statistic. That is going to be the evidence that you are going to put on the table. All right. So the test statistic is the evidence obtained from the sample data. It's Z equals X bar minus mu sub 0 divided by sigma over square root over n. Now, for one population mean and for the Z test, we use this formula, but it will change based on the different studies that we will learn in the later chapters. Okay, and then on the next slide, in step 4, we use these two approaches to come to a decision, the critical value approach and the p-value approach. In the critical value approach, we come up with reject regions on the normal curve, on the normal probability curve. If it is a two-tailed test, the reject regions are on the two ends of the curve and the do not reject region is at the center. If it is a left-tailed test, then the reject region is to the left of the curve, and if it is a right tail test, reject region is on the right and the do not reject region is to its left. And the critical value is really a Z value, right? This critical value is a Z value, Z of whatever your significance level is. That's what the critical value is. Now, if it is a two-tailed test, however, you have to divide your alpha into two equal parts and distribute to both the reject regions. All right. So for a for a two-tailed test, you must divide alpha by 2 for two-tailed test. All right, and then once you find the critical value, in other words, once you find your critical value, you will bring your test statistic and see where it falls relative to that cutoff. If it falls in the reject region, then we reject the null hypothesis. If it falls in the do not reject region, then we will not reject the null hypothesis. So after we find our critical values, we will bring our test statistic and we will have to see where it falls, in which region it falls relative to that cutoff or the critical value that we found. For the p-value approach, we start with our test statistic value. All right, so we start with our test statistic value. There are no reject and do not reject regions as in the critical value approach. In the p-value approach, there are no do not reject regions, but we take our test statistic and we place it on the curve and we find the area or the probability value. All right, the probability value or the area of to the right or to the left or on both sides of the curve. Again, that will depend on whether it's a two-tailed test or a left-tailed test or a right-tailed test. If it's a right-tailed test, the p-value will be to the right of whatever your test statistic value is. If it is a left-tailed test, then the p-value will be towards the left of whatever your test statistic value is. And if it is a two-tailed test, then the p-value is the sum of the area of the negative z-value and a positive z-value. In other words, what you're doing is you will find a p-value on one side wherever your test statistic falls, but you will have to double it up, all right, before comparing it with alpha. Okay, so step 5 says if p is less or equal to alpha, reject null hypothesis, otherwise do not reject null hypothesis. Whereas for critical value approach, step 5 says if the value of the test statistic falls in the rejection region, reject null hypothesis, otherwise do not reject null hypothesis. And then finally is to interpret the results of the hypothesis test. All right, the hypothesis test is exact for normal populations and is approximately correct for large samples for non-normal populations. Now we will talk about performing a hypothesis test when the population standard deviation is unknown. So when the population standard deviation is unknown, then we have to use S or the sample standard deviation for our calculations, and hence we cannot use the Z distribution. We will have to use what's called the T distribution and the T curve. So the hypothesis test when sigma is unknown is called the t-test procedure. It's going to be called the t-test procedure. And it works very similar to what we learned when finding the confidence interval when the population standard deviation is unknown. All right. So hypothesis test for one population mean when sigma is unknown. The way we find our p-value in this case is we have to estimate from the p-value from our table. All right. If you are using the table, then it is an estimation. You will never find the exact value because the t-table is a truncated table for a limited number of sample sizes, that is DFs, and also for just some special alpha values, correct? I will work through an example and show you how we work through a problem of performing a hypothesis test when sigma is unknown using the t-test procedure. Okay. Now here are the steps for performing a hypothesis test using the one mean t-test procedure. We use this procedure when the population standard deviation is unknown. When sigma is not known, we cannot use the z distribution because the z distribution uses the sigma in its formula, right? So we wouldn't be able to calculate the z value if the sigma is unknown. If it is unknown, then the only option we have is to use the sample standard deviation. In other words, we have to use S in our formula. All right, use S, and we cannot use, of course, in that case, we cannot use the Z distribution. We will have to use what's called the T distribution. S being the standard deviation, and we have to use the T distribution. And for the T distribution, as we talked before, the T distribution has a distribution for every sample size out there. So it operates on the basis of DF. DF is the degrees of freedom, which is for a one mean population. It is or rather for a one population mean, DF has a formula n minus 1, in other words, sample size minus 1. All right, so the steps essentially are the same. The null hypothesis statement is the first step, null hypothesis, and the alternate hypothesis statements. It's stated the same way as in the z-test procedure. Step 2 is to decide on the significance level. In step 3, the formula we are using is for the t test statistic. So t equals x bar minus the mu sub 0, which is the null hypothesis mean, divided by s over square root over n. And then in step 4, we use these two approaches, the critical value approach and the p-value approach, but we refer to the t-table instead of the z-table. All right, it says here, use table 4, but this is actually the t-table that we must be using, the t-table. And then we take a decision. We do the analysis from the curves. If it's the critical value approach, we check whether our test statistic falls in the reject region or do not reject region. And if it is the p-value approach, then we find our p-value for our test statistic, and then we compare the p-value with alpha. If it is less than alpha, then less or equal to alpha, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. And finally, in step 6, we interpret the results of the hypothesis test. If it is an application-based problem, then we will have to interpret it in the context of that problem.